Well, I'm going to talk about induction. And induction takes some getting used to. It certainly seems very strange at first and awkward. But once you get used to it, it becomes very natural. So we'll try to go through some examples step by step to get you accustomed to this way of thinking. Now, I found this page on the internet. If you do a Google search for Purple Math Induction, you'll find this page. I like this page because it does go through some examples really step by step. Okay, so we have some introductory material here. Here's a description of the components of an induction proof. First, you have to state what you want to prove. Now, that's always true when you want to prove something. You always want to put up front the statement that you want to prove. Second, there's a beginning step. This is also called the base case. Then the third is the assumption step, and I'll explain what that means later. And last is the induction step. Okay? So what do these all mean? So here's an example, very standard example in showing induction. You may observe by trying several cases that if you add the numbers from 1 to n, you get a total that equals n times n plus 1 over 2. Try it. Let's say n equal to 4. 1 plus 2 plus 3 plus 4 is going to be 3 plus 3, 6 plus 4 is 10. And if I plug 4 into this formula here, I'll get 4 times 5, which is 20, divided by 2, which is also equal to 10. Okay, so this formula checks out when n is equal to 4. And in fact, you can try any positive integer n and get that the formula works. So here's the formula stated. And this is the formula that we're going to state up front. Now, we've tried a couple of examples and it seems to work, but we want to prove that it works for all examples. And that's what induction is going to do for us. All right, so we start out our proof by stating what we want to prove. And Purple Math uses this technique of labeling the statement by a star. This is a good practice and is often used in mathematics. Okay, so this is what I want to prove. I can't assume this. This is where I want to end up by the time I finish my proof. Okay? Now, if you recall up here, I said there were 4 components. Next is the beginning step, or what I call the base case. All right. Question. So we want to know whether this is true for every n. First of all, it should be true for at least one n. Well, in fact, if you try n equals 1, it works. If n equals 1, there's only one term on the left-hand side, which is 1. And if I plug n equals 1 on the right-hand side, I get, as they show here, 1 times 2 over 2, which is equal to 1. So the formula does work for n equals 1. That's the first component in an induction proof. You have to show that your general formula is true for a specific value of n, and usually you take n is equal to 1. Okay? All right, so now that's the second step. Third step is the assumption step. All right, now here's where it gets a little bit tricky. We want to prove this for all n, and we've shown it works for a specific n equal 1. We're going to assume that it works for n equal to k. Right? So this k, we know that k equals 1 works. We're going to assume that it works for n equal to k. And what we want to show is that if we can assume it works for n equal to k, if we can use that fact to conclude it also works for n equal to k plus 1, then it will work for any value of n. Why is that? Well, if it works for n equals 1, and if it works for n equals 1, and we can prove that n equals 1 implies n equals k plus 1, that means that n equals 1 will imply n equals 2. Once we have n equals 2, then assuming n equals 2, we have n equals 3. So from n equals 2, we can get n equals 3. Okay. Once we have n equals 3, since we know that if n equals 3 is true, then it also works when n equals 4 is true. So you're laddering your way up through all the integers. So here's the key step. You have to assume that it works at n equals k and show that it will also work at n equal k plus 1. Okay. All right. So to show that it works at n equal k plus 1, let's plug in n equal to k plus 1. Then the left-hand side of our star is the numbers from 1 up to k plus 1. Now remember, we're assuming that it's true when n is equal to k. What do we have when n equal k? Well, we only have the first k numbers. Okay, so what we're going to do is separate out the first k numbers. Now, since we're assuming it's true for n equal k, I can replace this sum of k numbers with my formula star when n equal to k. All right, that's the key step of reducing the k plus 1 step, simplifying it by using the k step. Okay. All right, so now we're going to do some arithmetic. At this point, we can put the last term over a common denominator. We can combine it with the other terms. Okay, so now here you have k times k plus 1 from the first part, plus 2 times k plus 1 from the second part. Now notice there's a common factor of k plus 1. So I can factor out the k plus 1, and then I have the k plus 1 multiplying the k plus 2. So this is what I get, k plus 2 times k plus 1 over 2. Now notice k plus 2 I can write as k plus 1 times k plus 1 over 2. Now notice what I have here. My formula in star was n times n plus 1 over 2. N times n plus 1 over 2. Now what I have here is k plus 1 times k plus 1 over 2. This formula is exactly the same thing as what you get when you plug in k plus 1 for n. All right? Look at this formula. Replace n with k plus 1. What do you get? Here you get k plus 1 here. Here you're going to get k plus 1 plus 1. That's k plus 2. Okay? So if I replace k plus 1 in this formula for n, I get exactly this formula. What does that mean? That means that I've proven my formula star for n equal to k plus 1. Right? And that's exactly what I wanted to prove. I wanted to prove that if I assume it's true for k, it will also be true for k plus 1. Okay? Now that's just one example. I'm going to skip to page 3. You can read page 2. I think page 3 is more useful. Here's some more examples where the procedure is worked out. Right? So here's an example of, we want to prove this statement here. Prove that if n is bigger than or equal to 1, 2 plus 2 squared plus 2 cubed plus 2 to the 4th, blah, 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 plus 2 to the nth equals 2 to the n plus 2 minus 2. All right, now remember the steps that we took. We have to show that it's true for at least one n. So let's let n equal to 1. If n equals to 1, the left-hand side is 2. The right-hand side is going to be 2 to the squared, which is 4 minus 2 is equal to 2. Okay. So in fact, this formula works when n equal to 1. So that's what's verified here. The formula works when n equal to 1. Now we're going to assume the formula is true when n is equal to k. All right. So that means that I can replace n with k, and I'm assuming this is true. All right. Now I want to see if I can prove the same thing is true with n equal to k plus 1. All right, so I'm going to replace n with k plus 1. Now you can choose the left-hand side or the right-hand side. Usually you choose to plug it into the more complicated side. So I'm going to replace the n with k plus 1 on the left-hand side. And this is what I get. Now I recognize the first part from my n equals k case. For my n equals k case, that's what I had here. Now, since I'm assuming this formula, I can replace this part with the right-hand side over here. That's exactly what's done here. This part of the formula is replaced by this expression here. Okay, so that's how this is obtained. Now we want to do some algebra. We want to combine these terms. Here we have a 2 to the k plus 1. Here we have a 2 to the k plus 1. That's 2 factors of 2 to the k plus 1. So we get 2 times 2 to the k plus 1. And the minus 2 stays the same. Now your exponent rules tell you that 2 times 2 to the k plus 1 is equal to 2 to the k plus 1 plus 1. Okay, which is the same thing as 2 parentheses k plus 1 plus 1 minus 2. Now compare this formula with star. What's the difference between this formula and star? Well, in fact, if I replace n here with k plus 1, it's exactly the formula I got here. So just to recap, what did I do? I started with the left-hand side of star with n equal to k plus 1, did some algebra, and I found the right-hand side of star with n equal to k plus 1. Okay? All right, let's do one more here. It's a very much similar pattern. For n greater than or equal to 1, we have this formula. I take the sum of 1 times 2 plus 2 times 3 plus blah, blah, blah is equal to n times n plus 1 times n plus 2 divided by 3. First thing to do, plug n equal to 1. Okay? So n equal to 1, I only go up to 1 times 2. So the left-hand side is actually 1 times 2. The right-hand side becomes 1 times 2 times 3 divided by 3, which is the same as 1 times 2. So the base case checks out. That's what we have here. Star holds for n equal 1. Now assume for n equals k. So that means that I can use this formula in my proof. I'm assuming for n equal to k. Now let's try to show for n equal to k plus 1. That means I take the left-hand side of star and replace n with k plus 1. If I do that, I get these terms. Now notice he put the dot, dot, dot. He wrote the second to last term in addition to the last term. And the reason that she did that was that this part is exactly what we assumed for n equal k. Notice that this part is the same as this part here. That means I can replace this part with this expression here, which is exactly what's done here. She's bracketed off the first k terms, and she set that equal to the right-hand side of my assumption. Okay. Now, of course, I still have the last term, so I need to leave that here. All right, now we have to do some algebra. What are the common factors? Well, here's a k plus 1, here's a k plus 2. Here we have a k plus 1, k plus 2 as well. Okay, so we have a common factor we can factor out. This is k plus 1 times k plus 2, and then here you have a k over 3, and here you can write 3 over 3, put it over a common denominator. Okay, so if you notice here you have k times k plus 1 times k plus 2 divided by 3, plus 3 times k plus 1 times k plus 2 divided by 3. That's the same thing as k plus 3 times k plus 1 times k plus 2 divided by 3. If we rearrange a little bit, we get k plus 1 times k plus 2 times k plus 3 divided by 3. Now compare this with my original formula in star. My formula in star was n times n plus 1 times n plus 2 divided by 3. Now if I replace n with k plus 1, I get exactly this formula. Okay, let's go through one more. This case we're going to prove an inequality. For n bigger than or equal to 5, 4n is less than 2 to the n. Now, in this case, we're not starting at n equal to 1. We're not claiming it works for all whole numbers, only for whole numbers bigger than or equal to 5. Okay, so our base case, our starting point, is going to be n equal to 5. Does this formula work for n equal to 5? Well, plug in 5 on the left-hand side. 4 times 5 is 20. Plug in 5 on the right-hand side. 2 to the 5 is 32. So yes, when n equal to 5, this holds. Now we're going to do our assume step. We're going to assume that star is true for n equal to k. So that's assuming 4k is less than 2 to the k. We don't have to prove this. This is what we're assuming. Now we're going to do our induction step. Let's let n equal k plus 1. What do I want to do? I want to plug in k plus 1 into the left-hand side here. Okay? So that's what I do. If I plug n equal to k plus 1 in the left-hand side, I get 4 times k plus 1. That's 4k plus 4. Okay. Now, my assumption tells me that 4k is less than 2 to the k. Now here I have 4k plus 4. So that means that 4k plus 4 is less than 2 to the k plus 4. What we do? We replaced the 4k here. I mean, we made this comparison, 4k less than 2 to the k. We add 4 to both sides. Okay? All right. Now we also have that k is greater than or equal to 5. So that means that 32 is less than or equal to 2 to the k. Now you may ask, why is she doing this? Well, what do we want to prove? We want to show that this left-hand side, 4k times k plus 1, is less than 2 to the k plus 1. All right. Now on the right-hand side, we have 2 to the k plus 4. Then we want to show that 2 to the k plus 4 is less than 2 to the power k plus 1. All right. But when k is bigger than or equal to 5, 4 is less than 32, which is less than or equal to 2 to the k, because k is bigger than or equal to 5. So that means this right-hand side here is less than, since 4 is less than 2 to the k, the right-hand side here is less than 2 to the k plus 2 to the k. Okay, that's 2 times 2 to the k. That's the same as 2 to the k plus 1. All right, so what do we have here? We replaced k plus 1 in the left-hand side of star. We showed that that's less than what you get when you take the right-hand side of star and replace n with k plus 1. So we've proven the result, and that proof is finished. All right, I guess there is one more we can do here. All right, here's another statement that's neither in inequality or equality. Here's just a general principle. For all n bigger than or equal to 1, 8 to the n minus 3 to the n is divisible by 5. Okay. So let's try this. We want a base case. Let's try when n equal to 1. When n is equal to 1, then we have 8 to the n minus 3 to the n is the same as 8 minus 3, or 5, and that's divisible by 5. So we've shown the base case. Now we want to assume for n equal to k. That means that 8 to the k minus 3 to the k is divisible by 5. We're assuming this. Now what are we going to do? We're going to plug in k plus 1 into the left-hand side of star. Okay, what do we get when we get that? When we do that? Here we have 8 to the k plus 1 minus 3 to the k plus 1. All right, let's do some algebra here. And this is a little bit tricky. What's done here is adding and subtracting 3 times 8 to the k. All right, so and the reason that you do that is that you can group the first two terms, and you can group the second two terms. Okay. Now this is really a trick. It's really quite clever, but you can see that, we'll see that it works. What happens when you group the first two terms? Well, you have 8 to the k times 8 minus 3. Factor out a common factor of 8 to the k. Then what about the second two terms? Well, they have a common factor of 3. So here I have 8 to the k times 5 plus 3 times 8 to the k minus 3 to the k. Now why is this good? Because 8 to the k minus 3 to the k, that's our expression in our assumption. we already are assuming that this is divisible by 5. So what do we have? We have one term here that's obviously divisible by 5, plus another term that's divisible by 5. That means the entire expression is divisible by 5. So we have that the right-hand side of the expression star is true when n is replaced by k plus 1. Okay, that gives us the end of the proof, and that's what we wanted to show. All right, let me just introduce this document here. And I'll have to make it a little bit smaller. So this is another example, and you can see it follows the same procedure. So actually, this is the one that we did at the beginning of Purple Math. You have the base case and the induction step. Assume the formula is true for n equal to k. Then here's the left-hand side for k plus 1. And then work some algebra using the assumption that the formula is true for k. You get that the right-hand side with k plus 1 is achieved. Okay, so this is really the very same thing as the first example of Purple Math. Okay, hopefully you can get some idea from these examples and start to try some of these other problems that we can do. Okay, that's it.